All right, let's dive right in. Today, we are going to talk about the fundamental physics that, and this is no exaggeration, makes our entire modern world possible. We're talking about semiconductors.
Seriously, just for a second, take a look at the room you're in. Just notice all the technology.
Maybe you're holding your phone in your hand right now.
Or hey, maybe you're watching this on your laptop.
The point is, all these devices, from the little controller in your smart lights to the incredibly complex computer on your desk, they are completely woven into the fabric of your life.
But have you ever really stopped to wonder what makes it all work? What is the secret sauce, the one core principle that allows all of this incredible technology to even exist?
Well, that's what we're here to do. We're going to break it all down. We'll start with the big idea of controlling electrons. We'll look at the old tech we ditched, and then we'll dive right into the atomic playground to see the rules of the game. After that, we'll sort materials into their teams, see how we can actually hack them to do our bidding, and finally bring it all back to that amazing device in your hand.
Okay, so let's get into it. At its absolute core, our entire digital world boils down to one simple yet really profound goal: making these unbelievably tiny particles called electrons do exactly what we want when we want. And that right there, that's the very definition of electronics. See, it's not just about electricity flowing wildly, it's about the precise surgical control of that flow. You can think of it like being the conductor of a massive orchestra of electrons, telling them exactly how to move to get useful things done, like switching a circuit on and off billions of times a second.
Now, figuring out how to control electrons like that, it sparked a massive technological revolution. You see, before our sleek modern devices, the world of electronics looked, well, it looked a lot bigger and a whole lot hotter.
Early electronics depended on these clunky glass vacuum tubes. They were huge, they guzzled power, they got incredibly hot, and honestly, they were super unreliable. The real revolution happened with the invention of solid-state devices. These tiny, efficient, and unbelievably reliable little components made from semiconductor crystals. This was the moment electronics went from the size of a room to the size of your pocket.
To really understand this incredible leap, we have to shrink our perspective. I mean, way down. We need to go inside the atomic playground itself and understand the fundamental rules that tell electrons how to behave inside these materials.
And right away, we run into a huge problem. You know, early models of the atom pictured it like a tiny solar system. But wait a second. If a negative electron is orbiting a positive nucleus, basic physics says it should lose energy, spiral inwards, and the whole atom should just collapse on itself. But obviously the chair you're sitting on isn't collapsing. So what in the world was going on?
Well, the physicist Niels Bohr basically solved this whole puzzle by coming up with 3 new rules for the atomic game. Rule 1, electrons can't just be anywhere. They have to exist in specific, fixed orbits, kind of like designated lanes on a highway. Rule 2, as long as an electron stays in its lane, it doesn't lose any energy. It's perfectly stable. And Rule 3, an electron only absorbs or releases energy when it makes a quantum leap from one lane to another. And just like that, he explained why atoms don't just collapse. So, here is the absolute key takeaway from all of that. For all the electrons buzzing around an atom, the only ones that really matter for conducting electricity are the ones in the outermost lane. These are called the valence electrons. They're the most loosely held, and they are the ones that determine absolutely everything about a material's electrical properties.
And based on how these valence electrons behave, we can basically sort every single material in the entire universe into one of 3 teams.
And this table just lays it out perfectly. On one team, you've got conductors, like copper. They have very few valence electrons that are just itching to move, creating an open superhighway for electricity to flow. On the opposite team, you've got insulators, like glass. Their electrons are locked down tight, a total brick wall. And then there's this very special case in the middle, semiconductors, like silicon. They're like a locked gate. By themselves, they don't conduct well, but if you have the right key, you can open that gate right up. So we've got this locked gate. The next obvious question is, where's the key? How do we take this weird material that's kind of useless on its own and turn it into one of the most important substances in human history? Well, we hack it. And this hack has a name. It's called doping, and it is no exaggeration to say that this process is the single most important technological trick of the last century. It's an incredibly precise technique where we intentionally sneak in tiny amounts of impurities into a pure silicon crystal. And by doing that, we turn that locked gate into a perfectly controllable switch. Now, doping comes in 2 main flavors. With N-type doping, N for negative, we add an impurity that brings an extra electron along for the ride. That extra electron is free to move around and carry a current.
Then there's p-type doping, P for positive. Here, we do the opposite. We add an impurity that's actually missing an electron, which creates an empty spot or a hole. This hole acts like a positive charge, and electrons can jump into it, which makes it look like the hole itself is moving. The amazing thing is, in both cases, we've turned our boring insulator-like silicon into a great conductor.
Okay, so let's bring this all back home. We've gone from your phone all the way down into the atom, and now we're back with this incredibly clever trick called doping. So, why does this all matter so much?
Because every single critical component of modern electronics is built by arranging these two types of doped silicon in clever ways. A diode, that's just an N-type and a P-type piece stuck together. A transistor, the fundamental switch that powers all computing, that's just a sandwich of NPN or PNP materials. And microprocessors? Well, those are just billions of these tiny transistors packed onto a single tiny chip.
So the next time you pick up your phone, just remember, what you're holding isn't magic. It's the incredible result of our deep understanding of atomic physics and our ability to manipulate materials at the most fundamental level imaginable. This knowledge is, quite literally, the bedrock of our entire digital age.
You know, we've built an entire world on our mastery of silicon. It's absolutely incredible. But it does make you wonder, right? With our understanding of materials and quantum physics growing every single day, what new materials and what new hacks are out there just waiting to be discovered? What's going to come after silicon?